Jnanam Paramam Dheyam. Knowledge is supreme.
Welcome to this course on advanced transition metal organometallic chemistry. As a part of our discussion on organometallic catalysis reaction, we have been discussing an important reaction, which is asymmetric hydrogenation reaction. And in this context, we have discussed about the Nairi catalyst in the previous class, and in that discussion what we had observed that Nairi catalyst is very much similar to that of the Strock-Osborne catalyst, which is nothing but L2 rhodium bisolvated cationic complex, which in which L is a chiral phosphine based chiral ligand, rhodium and solvent is the solvent coordinated to the metal center. And in that sense, Nairi's catalyst is also of the similar type. L2 means L being a chiral ligand, chelating phosphine ligand, rhodium bound to 2 carboxylate moieties. Now, what we had seen that in Nairi catalyst is extremely good for enantioselective selective hydrogenation, and these chiral PPH2 phosphorus bound PPH2 moieties exert van der Waals interaction on the rhodium center, which in turn transmit the chirality onto the substrates, which are bound to rhodium after displacing the carboxylate. And we had seen how a heteroatom assisted carbonyl compounds can be selectively hydrogenated to alcohol in an enantioselective fashion using this Nairi catalyst. So, this was a wonderful demonstration of applications of Nairi catalyst, and what we had seen that the chelation of the heteroatom, the distant chelation of the heteroatom along with the carbonyl moiety was very much important in being enantioselectively obtaining the hydrogenation product. Continuing our discussion further on the Nairi catalyst, we are going to look up some more examples which sort of highlights why this Nairi catalyst have been so much appreciated in the domain of asymmetric hydrogenation catalysis. I must note that Nairi has been conferred the Nobel Prize for his work on this asymmetric hydrogenation catalysis, and that is why his catalysts are so famous and have been recognized duly by the scientific community. The asymmetric hydrogenation, as was observed in our previous discussion, was due to this chelation of the distant heteroatom, and one can sort of extend the concept from a carbonyl with distant heteroatom to the substrates like diketones, and there one can see that the stereo induction arises due to chelation of the carbonyl groups. So, the main principle or the main success of Nairi catalyst in asymmetric induction is due to the chelation of carbonyl group and the heteroatom of the substrate to the binap, ruthenium unit, and substrates like 1,3-diketone, beta ketoesters or amino ketones are also enantioselectively hydrogenated. Suitable substrates like 1,3-diketone, beta ketoester, amino ketones are enantioselectively hydrogenated. So, this is beautifully illustrated by this equation given over here. One 3-diketone reacting with R binap RuCl2 in presence of hydrogen 70 bar gives alcohol R 99% E at 10% conversion, and which, if allowed to react more with hydrogen, then so the first obviously is the reduction of the diketone to alcohol and ketone. So, one of the group gets reduced, the other chelates, but if one continues with the hydrogenation, then both the carbonyl compounds are reduced to alcohol, and the stereochemistry of the alcohol is RR 100% E and little bit of the meso product like OH, and the ratio of this RR to meso is 99:1. So, one can really appreciate the power of this Nairi catalyst in terms of achieving this enantioselectivity. So, using this concept of chelation of carbonyl, the group getting reduced with one of a distant heteroatom can be successfully used for the diketones or the ketoester substrates, where the first one of the carbonyl compound is reduced in high selectivity about 99% E, and then subsequent treatment with hydrogen reduces both the carbonyl, giving the RR product in 100% E and about 99:1 selective product selectivity towards the RR compound as opposed to the meso compound. So, one can sort of appreciate the power of these the diketone Nairi catalyst on diketone substrates. So, Nairi catalyst can also be used to produce beta hydroxycarboxylic ester. So, Nairi catalyst can also be used to produce beta hydroxycarboxylic esters which are important as intermediates towards many organic and natural products, and this is beautifully illustrated by these beta ketoester substrates, which is OR dashed and R by NAP RUX2 H2 80 to 100 bar, giving O R OH star, and the yield is over 95% and selectivity over 98%. So, one can see this chelation concept of heteroatom chelation bound in distant to the carbonyl being so effective in using Nairi catalyst for producing alpha hydroxycarboxylic esters, which are important components of many natural products. Now, this chelation can also be used to do an anti-selective catalysis with halides. So, halogen atoms in substrate can also suitably anchor the catalyst through chelation to give high anti-selectivity. In substrate, can suitably anchor on catalyst through chelation to give high anti-selectivity. And this is beautifully illustrated by the example bromo or binap ruthenium X2 plus hydrogen bromide OH R. So, 97% yield and 92% E. Now, only the fact that only ortho-halo substrate undergoes hydrogenation and the para and the meta does not give hydrogenation, that sort of underscores that the importance of chelation in being able to hydrogenate. The fact that meta and para isomers do not hydrogenate, it highlights the importance of chelation. So, this is a important point in explaining the high NNT selectivity observed in case of Nairi catalyst, that there has to be heteroatom bound chelation distant to the carbonyl moiety, which results in higher chirality transfer leading to higher NNT selectivity. So, in substrates where such chelation is not possible, for example, the ortho and the meta and the para substrates, such kind of hydrogenation does not proceed at all, which further highlights the importance of chelation in hydrogenation reaction. Now, asymmetric hydrogenation with other catalysts has also been used for synthesis of many natural product. For example, have been successfully used in the synthesis of anti-inflammatory S-naproxen. Anti-inflammatory S-naproxen. And this is given as CO2H H2 S binap ruthenium R2 giving O methyl. CH3 CO2H. E is extremely high, 97%. And one interesting thing about Nairi catalyst is that Nairi catalyst is even superior to rhodium catalyst in hydrogenation, asymmetric hydrogenation reaction. So, this is an important aspect of Nairi catalyst. The binap ruthenium X2 catalyst Nairi 1990 is superior than rhodium catalyst in asymmetric hydrogenation. So, this is an important information, as here we have a catalyst which is based on ruthenium, and usually the rhodium is more catalytic active as it is called a magic metal, but here we have a ruthenium catalyst in form of niobium catalyst performing better than this rhodium based asymmetric hydrogenation reaction. So, another interesting trick is the enantiomer selectivity through carbonyl coordination, and we are going to take a look at this example individually. So, through steps. So, we have a chiral ancillary rhodium, the chiral catalyst plus the substrate hydrogen R NH COMe, that can react in two pathways. So, in which the substrate binds in one particular way, which is NH R CO2 Me rhodium P star plus H2. So, now the hydrogen comes and gives the same NH R CO rhodium hydride phosphorus and then CO2 Me overall plus. So, that in many steps gives CO2 Me hydrogen R NH COMe. Now, the other pathway is shown over here, in which the olefin binds in the different way, as is shown. Rhodium NH R CO2 Me bound to rhodium, overall it is a plus, adding hydrogen, but in a slow fashion for this particular enantiomer, giving rhodium hydride, phosphine, hydrogen O NH R CO2 Me, and this rhodium is bound to that. This is still monoionic, and then after several steps one can see the formation of ketone NH H CO2 Me and R. So, what we see, the configuration over here is S 95%, the configuration over here R is 5% and this hydrogen addition is slow. So, this is how the stereo differentiation occurs in this complex. The carbonyl group assists in stereoselectivity by anchoring with catalyst. So, what we see is that this niotic catalyst is successful because of its ability to carry out facial discrimination, and that is why it can carry out selectively all these asymmetric catalysis reaction. So, here is another nice example on asymmetric catalysis reaction that we will be talking about is Ar hydrogen C NH AC C O2H Ar equals 3 4 C3 C6 H3 OH whole 2 DIP AMP equals O PH O Me phosphorus pH, this is a chiral entity P, this phosphorus is also chiral pH PHO Me. So, this is the diamp ligand and this is used for preparation of L-DOPA, which is our diamp rhodium salt 2 plus 50 degree centigrade 3 bar in presence of hydrogen gives the two isomers in highly enantiopier form CH2Ar NHAC CO2H and H, this is 97% and the other isomer thus is C H C H2Ar C O2H NHAC, and this is formed in 3% yield, and this is a useful method for preparations of L-DOPA. So, with this I would like to conclude our discussion on asymmetric hydrogenation reaction, and what we have looked at is the reason behind the tremendous success of asymmetric hydrogenation reaction in regard to chirality transfer, and what we had observed is that there is a chelation of a distant heteroatom bound to the hydrogenation moiety, which can be a carbonyl, which allows for such enantioselective discrimination towards one product over the other. Now, we had also looked at the substrates which will have such ability to form such a type of chelation in terms of enantioselective discrimination, and we found that substrates like diketones, beta keto esters all can be non-selectively hydrogenated with Nairi's catalyst to give the corresponding hydrogenated product. We have also seen alpha bromo acetoxybenzene can also give such hydrogenated product. Then that primarily is because of the presence of the bromo moiety on the benzene atom or bromine having lone pairs which can chelate to the metal complex or anchor to the metal complex and help in NNT selective reaction. So, with this I conclude today's discussion on asymmetric hydrogenation reaction, and we are going to take up another very interesting discovery in the next lab, which is this hydroformylation reaction. That also is a important reaction from industrial perspective. So, more on hydroformylation reaction when we meet next in the class. I sincerely thank you for your time and attention that you have given to me for being with me in this class, and I look forward to being with you in the next class where we take up hydrogenation in lot more detail. So, till then, goodbye and thank you.